Let's start with dealing with materials data collection, analysis, and interpretation. Assignment number 5. So let's discuss one reason. Suppose first question is suppose n random trials are conducted and the outcome of each trial is either a success or a failure. Which of the following distribution describes the number of successes in such trials? So for this, they have given the options as negative binomial distribution, uniform distribution, and exponential distribution. So if you see this question, like there are n random trials conducted. Random trials means there is no specific um, uh, methodology which they have followed, like sequence they have followed. They have just did it. Yeah, I just did it in a random fashion, like selecting a random color ball from the on kind of experiments. So what they're asking is like in each trial, so either success or failure is the outcome, which means like it is a Bernoulli trial. So that is what they're trying to indicate. Okay, so okay, in such experiment or the random trial, which of the following distribution describes the number of such successes in such trials? So, number of successes in such trials. Since it is like a success or failure, it is like only two outcomes are there. So for that, if you see, they are asking for number of successes. So by negative binomial distribution, deals with number of success after the trials or number of failures after the trial. So they don't just discuss success or failure based on the success or failure of each experiment. They need additional data like how many trials and all those things. For this number of success in such trials, the one which closely follows is the binomial distribution. So as I have stated, this uniform distribution, as we know, in a given interval, their output will be uniform. After that, otherwise it will be zero. So then exponential distribution, we know, like it is exponentially distributed. Yes. So it's a continuous one. It's not like it won't come into this consideration. So the only option is the binomial distribution. So let's discuss about what is this negative binomial distribution, because we have heard about this binomial distribution many times. But this negative binomial distribution is like not that much well discussed. Yeah, like they will be discussing, but not in detail. So let's discuss about this negative binomial distribution. Unlike the binomial, okay, what is negative binomial distribution? Unlike the binomial distribution, which focuses on number of successes, as we discussed in the first problem, until a fixed number of failures occur, the negative binomial distribution focuses on the number of trials required until a specified number of success has been achieved. So number of trials required to achieve a specified number of successes. So that is what negative binomial distribution is. So, in other words, we can put it in this way: like number of trials n needed to get rth success, like number of trials, like 10 trials required for third success, like that. And it helps. Otherwise, we can tell it like it helps in finding r success in x trials. How many successes in x trials? So x is the number of trial, and r is the number of success. So we can put the probability mass function in this way. P of x is P of x, where a random variable is equal to x. It's equal to x minus 1, the combination of x minus 1 to r minus 1, and p power r and q power x minus r. P is the probability of the success. For example, if I'm throwing a coin, like it's a probability of success is 0.5. Probability of getting head is 0.5, and probability of getting tail is 0.5. So probability of success P, and Q is the probability of failure. So it's 1 minus Q is equal to 1 minus P. So using this, we can determine the probability of rth success in n trials. So in coming problem, we will discuss, like once we solve the problem, you will understand it better. This is not into the assignment. Just I'm taking it from another book and we are solving this. Suppose a basketball player is practicing free throws. On average, he makes 70% of his shots, which means the probability of the success is 0.7. We want to know the probability that he will make five successful shots r is equal to 5. I mean number of success in the sequence of shots before missing three times. They're telling that he has missed three times in this success when while achieving this five success. So which means like the total number of shots x, the total number of trials is equal to 8. So x is equal to 8 and the number of successful shots is 5. So now how we can solve this problem is um, probability of x is equal to 5, sorry, 8 is equal to um, 8 minus 1 c minus 1 into 0.7 whole power 5 and 0.3 whole power x minus r, which is 3. So this is 7 c is 0.7% is the 3 multiplied. This can be written as 7 and 7 and 6 and 3. One star. So someone is going on 1 second. Hello, yes. Yes, please join this. This how I have started. Like we can discuss like in, next few questions. Like if you are having the doubts in the first page, we can discuss. That's fine. Okay. We were waiting for 10 minutes, but no one joined. Yeah. Anyway, let's continue. So in factorial, then minus of factorial. So it's minus this. So 3 factorial and minus 4 factorial into r factorial. So here, this we can cancel 3 to 6, 6. So this 35 only. 0.7 whole power 5 how much? So 0.7 whole power 5. So 35 and 70. That should 0.15. So probability that he will make five successful shots in the sequence of shots before missing three times. I mean, in total number when he throws eight times, probability of getting five successful shots is 15%. That doesn't mean. Let's go to the next question. That the joint probability mass function of the random variables x and y be defined as follows. Joint probability mass function they are given, where when p of x is equal to 0 and y is equal to 0, it's 0.2. So let's write it here. Two, seven, two, one, two, two. So so this is what it is given data. The conditional probability mass function we're asking probability of x given y is to the value of x. This is what the question is. Okay. To find this out, how can we solve this is we need to find probability x for x when y equal to 1. So it will be given by probability of so by probability of particular handwriting. It's equal to x. This is the x. Okay, y is equal to 1 divided by probability of y is equal to 1. So you have to find what is the probability of y is equal to 1. Then if we solve, if we substitute in this, we will get the answer for this. So for this, we already know um, y is equal to 0 or y is equal to 1. That's probability of comma the probability of 0 0 comma 1 and 1 comma 1. 0.3 plus 0. What is the probability of y is equal to 1? Now we can find the conditional probabilities. So, click on your sheet. So now we have to find probabilities. How is it that is given on the probability. Here we have two possibilities. When x is equal to 0, next the first will when x is equal to 0. Probability of 0 is equal to y axis. To z comma y right? Y. So what's the probability of x 0 comma probability of 0 comma 1 is 0.4 divided by probability of 0.5 equal to 0.8. Yeah. So next subdivision is when x is equal to 1. Probability of x is equal to 1. Then y is equal to given by probability of x equal to 1 plus y. Yeah. That means y can be solved by probability of 1 comma 1. What is the probability of 1 comma 1? Probability of 1 comma 1 is 0.1. And still 0.8 comma 0.2. So that is the answer. I think they have given it in the okay. It's the answers whatever they have given us in the fractions. So whatever it is closely matching is 4 by 5 comma 1 by 5. So in last question also distribution. I think you have got it right. I will explain the problem again. So they are asked for the conditional probability mass function when they are given y is equal to 1. When y is equal to 1, what is the conditional probability of x? For that, the formula is like p of x. P of x is equal to x. That is which we have to find out. Given y is equal to 1 is given by using probability mass function is equal conditional probability mass function is equal to p of x is equal to x is equal to x comma y is equal to 1. So we have two possibilities here. The x can take up the value of divided by p of y is equal to 1. Here the x can take up the value of either 0 or 1. So based on this, we have to like solve the further things. For that, first thing which you have to find is when the probability of y is equal to 1. So when we find this out, we have probability of y is equal to 1 has two possibilities when x is equal to 0 and when x is equal to 1. So probability of x is equal to 0 comma probability of x is equal to 0 comma 1 plus probability of 1 comma 1. Then we have combined it and we have got the probability of y is equal to. So from that, using the formula whatever we have discussed before, we have solved it. So let's go to the third question. The third question is in R, the density of the binomial function is calculated using a command. Okay, the density. Okay, let's discuss one by one. What? Yeah. So what one by what are other things we use? So in R, B binomial gives the binomial probability mass function. Um, when we use this command D binom, it calculates the probability mass function of a binomial distribution. And the syntax for that is uh, D binom of x, comma size, comma probability. Then in this x we have to specify the number of successes in the number of trials, given the probability of each success, sorry, each trial. Probability of success in each trial is the respective probabilities. For example, if I am throwing a coin 10 times and the size of the number of trials is 10, the number of successes like what I specific, like at least five success in 10 trials. So then probability of the success in each trial is 0.5 when I'm tossing a point. Then it gives the probability of getting exactly X successes in size given trials. Like for here it is like 5 successes in 10 trials with the probability of success being given. This is it used for giving the discrete outcomes with two possibilities for all the Bernoulli trial. Then this P binom, suppose we are testing a method uh, to make it like um, practical example, we can take this. Suppose we are testing a metal alloy. Each trial involves testing whether a sample of the alloy meets a certain strength threshold. Meets a certain strength threshold or falls below it, like whether it is crossing the minimum limit, means minimum requirement or not. And if it crosses, it is a success, and if it falls below it, it is a failure. You want to find the probability of getting exactly two samples out of five that meets the strength threshold. So your number of trials is five, and two number of success is like two. In five trials, they need two success, and probability of it is 0.8. So in using this D binom, we can specify 2 comma 5 comma 0.8. Even we don't have to specify like variable size and all, like you can directly give it and the answers will be provided based on this. And P binom is the binomial cumulative distribution function. So it gives the cumulative value rather than the exactly five successes like that. It gives like more like at least two success means it will calculate from two to number of trials, rest of the number of trials like that. So here is an example. Uh, it gives the probability of getting X or fewer successes in given trials with probability of success being P. Okay. So to find the probability of getting two or fewer samples out of five that meet the strength threshold, that can be given by like two or fewer sample means um, at most two, one, and zero. All these things has to be calculated. So for that, P binom two size five. Okay, two. Yeah. So 2 comma 1 comma 0 for all these things. If you use P binom, we will get the required answers. Bn binom is a negative binomial binomial mass function. It calculates the probability of the negative binomial distribution. It gives probability of achieving x success before size failures in a sequence of Bernoulli trials, with the probability of success being p. Okay, like before. Suppose we are testing the time until a metal alloy sample fractures. For example, each trial involves applying stress until the sample fractures or reaching a certain stress level without fracturing. Okay, so if I have a tensile strength value, like how much, if it crosses, it fails. If it doesn't crosses, uh, okay, like some sample after even after reaching it fails, but some samples doesn't fail. Like when it doesn't fail, it is success. When it fails, it is failure. So that is what the question is. You want to find the probability of the sample fracturing on the third trial given the probability of failure is 0.2. So probability of sample fracturing on the third trial given the probability of failure is 0. Okay. So the probability of fracturing on the third trial, there are three failures before success, um, is given by dn binom. So when 3 is the number of success here means failure success here, and we are taking number size means number of trials as 3 in 3. The probability of failure is 0.2. So in this way we will get the negative binomial distribution. So R binom is like generating a random variables variate from binomial distribution. It simulates n outcomes like based on the specification, and we can use this for comparison with our calculate experimental data. Yeah, if when we correlate, if they match 1 to 1, we can regard our data as we can tell our data as normal distribution. Otherwise, we don't tell it as normal distribution. So for that, we need to generate in a given interval data set which follows the random binomial distribution. So this can be for this R binom can like similar to R binom n norm, then n poise. So all are available because for each and every distribution you can generate your own data set in the given interval. For example, suppose we want to simulate 10 tests of metal alloy where each test involves 5 trials to check if it meets a certain strength threshold. We can simulate the number of success in each test. So for this, we need we are going to simulate a 10 test. So with 5 trials. So yes. So probability of success is like um, probability that it success in each test is 0.8. So using this, we can generate some 10 test. Uh, each test involving 5 trials. So what is okay? Let's also discuss about the geometric function. Why we are discussing? We have answered this three. No. So let's come to the question. In R, the density of binomial function is calculated using the command density of binomial function is calculated using d binom. So this is for cumulative. This is for negative binomial. This is for generating random variates in the binomial distribution. This gives exactly the binomial function or the probability mass function. So there is an answer for that. Okay, before going to the next question, let's discuss something about the geometric function distribution and hypergeometric distribution. So this one we have discussed in the last class also, or assignment when where we have solved. The geometric distribution is a probability distribution that models the number of independent Bernoulli trials required to achieve the first success. Like it is like sometimes we will be having like how many attempts person has to take to clear the UPSC exam. The clearing means it's a first success. So those kind of problems will be discussed that can be solved using this geometric distribution. This is often used to describe the number of trials needed before observing a particular outcome. So this is useful in many experimental hypothesis where we hypothesize something and we try to achieve it. So some of the characteristics of this geometric distribution are it involves a sequence of independent trials. So the trials, whatever we are doing, is independent. Each trial has two possible outcomes. It's Bernoulli trial, like success or failure. The probability of success P remains constant across all trials. As we have discussed, it's independent trials. The probability of success remains same for all the trials, which means like it is memoryless property. The distribution is okay, yeah. The distribution is memoryless, meaning the past trials do not affect the future ones. So when probability of achieving n first success in n trial is given by P is the probability of success into 1 minus P whole power number of trials minus 1. So, and when they are asking like how many success are achieved or one second. How many trials are required to achieve n success is given by 1 minus P whole power n, and mean of this is given by 1 by P, variance is 1 by P divided by P square. These are all useful while solving the problem. So just if you know it will be good. Okay, let's go to the fourth question. In the course, we have discussed the atom probe technique and the distribution that results in the process during the evaporation and detection of atoms. From the probe volume, let's see, we know the probe will be like a conical. It contains several atoms like I, J, like the total, okay, from the probe volume, let M atoms evaporate. So M atoms is evaporating and hitting the detector. The efficiency of the detector is Q. Efficiency means it is like number of atoms detected divided by number of atoms evaporated. So number of atoms detected is N, divided number of atoms evaporated is M. So using this value, the composition is estimated. So yeah. The number of evaporated atoms M during the process before N atoms are detected. Okay, this is like as you have seen in the geometric function, right? Number of atoms N, number of success N atoms detected before when in given like M trials or M atoms are being evaporated. Follows which probability distribution? Like we might think it is a geometric distribution, but once we go back and see their characteristics, it involves sequence of independent trial, which means like the past trials do not affect the future one. But if you see here, once some atom is being evaporated, it is not conservative anymore. Like the number of atoms is reducing, volume is reducing, which means like the previous trials affect the future trials, probability of the future trials. So this is not geometric distribution. This will fall under the category of hypergeometric distribution. The hypergeometric distribution models the probability of obtaining a certain number of success. They are denoted as K. It depends in a fixed number of draws. So number of success in a fixed number of draws from a finite population without replacement. Finite population means like here the atom probe is a finite population where number of atoms is constant. Sorry, number of atoms is n, and it will be keep on decreasing. Based on that, the probability of detecting an atom also decreases. So the characteristics are it involves sampling without replacement. This is a major point. the population size and since n is finite, each draw changes the probability of success for subsequent draws. This is very evident from the without retest. Okay. Typically used in situations where population size is small relative to the number of draws and where the probability of success changes as items are born. Okay. These are the characteristics. Let's go to the fifth question. Okay, I think I have not answered the fifth question. Sorry. So the fourth question is they are asking m atoms are evaporated out of which the okay n atoms are detected out of from the m evaporated atoms. So though it is closely related to geometric function, since it's a finite term, it falls into the hypergeometric distribution. So based on the discussion done before, the expression to calculate, okay, well, let's go to the fifth question. The expression to calculate the probability distribution of m evaporated atoms before n atoms are detected by detector in previous problem 4 is, okay, they're asking calculate the probability distribution of m evaporated atoms before n atoms are detected. So here, um, they're asking us to find the probability distribution. It's like n successes out of before m trials. So this closely resembles the negative binomial distribution, where we have seen number of successes or number of failures before the first failure or first success. So similar to that, out of number of trials, m trials, the n atoms have n number of atoms have been detected, and otherwise we can put it like for n atoms to get detected, how many atoms have to be evaporated. So this is like atom probe technique. The digital efficiency or the probability of detecting an atom is discussed is defined based on this. So for this, just we have to consider this as negative binomial distribution. Yes, I understand. Like though the atom probe technique is finite source, finite number of atoms are available, and each trial the probability is changing. Still, we are here. We are using negative binomial distribution because here we are not accounting for the how to say. Um, One second. Okay. So, unlike the last question, which okay, where they have asked like number of atoms during number of atoms to be evaporated in the during the process before n atoms are detected at the detector. So, like unlike that, here they are asking just asking like what is the what is the probability that n atoms are being detected before like how many like how much number of atoms have to be evaporated to get n atoms. No, second, I'm just confusing it right. Okay, let me discuss this clearly in the next slide. Um, I have compared it. One second. So here it is clear, right? Like how many atoms have to be evaporated to get the n atoms detected. This follows negative binomial distribution. So for negative binomial distribution, the probability mass function is given by P of x is equal to x is given by x minus 1 combination of x minus 1 to the r minus 1 p power r q power x minus r. So here X is nothing but M atoms being detected, and what else? Yes. Then number of atoms detected is R. Or atom. So here the probability is given by the efficiency. So don't mistake this Q and this Q. Like the Q is represented by the efficiency, which is nothing but the probability. It's given by N by M. So let's use Q in the case of P. So it's Q power N and 1 minus Q power minus, sorry, 1 minus Q power N minus. So if we just check which one is matching close to this. We expand this M minus 1 factorial divided by N minus N factorial N minus 1 or factorial into Q power N into 1 minus Q power minus 1. So this is matching with the second option. So first thing we have to understand is like in which case it is binomial negative binomial distribution and in which case it is hypergeometric function. Okay, so this we will try to elucidate clearly in the coming this slides. So when we use hypergeometric function when we have fixed population size, we are sampling without replacement, and means once a number of atom is evaporated, it is not available for the next trial. We are interested that in number of successes, uh, number of detected atoms, out of which fixed number of trials. Okay, we use negative binomial distribution when we have sequence of independent Bernoulli trials. We consider them as like independent Bernoulli trial, like getting detected is success, getting not detected is failure. So each atom being detected is considered as independent Bernoulli trial. We are interested in number of trials, operations, and until the specific number of successes n occur. Okay, each trial has same probability of success, which means like the detector efficiency is not going to change. So evaporation process follows. I would say in other way, like the evaporation process, all those things follow the evaporation process and detection completely follow the hypergeometric distribution because number of atoms being evaporated, the probability is depend on the size of the population, and it's doing without replacement, so it follows the hypergeometric distribution. When we discuss only in terms of the detector where the detection efficiency or probability of detection is constant, which is Q, which is equal to N by M, we can use the negative binomial distribution. So in context of APT, hypergeometric distribution for number of atoms, number of evaporated atoms until n atoms are detected. So evaporation process considering a fixed number of atoms in the probed volume. So this is when we use the hypergeometric during the evaporation part, and negative binomial distribution for the number of trials until n atoms are detected in detector. So considering each trial the same probability of detection Q. So if you know the exact number of atoms in the volume under sampling without replacement, hypergeometric is more appropriate. If you are looking at the sequence of independent trial until a certain number of atoms are detected, negative binomial can be used. So I think this is made clear. Like if you still have doubt, I can explain again. I just explain this slide again. In the context of APT, when we are discussing about the evaporation process, the number of atoms is finite, and the evaporation process is like selecting an atom without replacement. Hence, the success, hence the probability of the trials affects the probability of the future trials. So we use hypergeometric distribution, and then when it comes to number of atoms being detected, we use the negative binomial distribution. Just a minute. So, for number of, sorry, the negative binomial distribution is used in case of detector, where the detector efficiency is constant, which means that the probability of getting detected is n by m is constant. We use number of atoms being detected out of m evaporated atoms is given by the negative binomial distribution. So with this, we will go to the sixth question. So sixth question is like, it is known that during manufacturing, the probability that a manufactured solar panel will be defective is 10%. Okay. Probability solar panel being 0.1. Assume that there are 18 solar panels that are randomly chosen. Assume that these are all independent, that these are independent samples. We want to calculate the probability that out of these 18 samples, 4 or more samples are defective. Which of the following code or snippet will give the answer? Okay. So the question is like, we need to find out the at least 4 samples out of 8 is defective. At least 4. So it includes 4, 5, 6, 7, 8, 18. The size is 18. Out of that, they're asking from 4 to 18 all the um, why not all we have to calculate the probability for all those things, and we have to make it cumulative. And probability of success means for probability of the panel being defective is 10%, just feasible to generate. So if you see the first option, sum of b binom 4 is to 18. This 4 is to 18 gives takes the value from 4 to 18, including 4 and including 18. So size is, as we have seen, the b binom, this is number of success in size x, size gives the probability. This is the syntax. So out of which we have specified the number of successes from 4 to 18. Like 4 samples being detected to 18 samples being detected as defective. Then size is 18. We have taken 18. And P is the probability of success in each trial. 0.8. So sum gives the sum of the each values, like starting from 4 to 18 gives will be summed, and the answer will be given. So the first option is correct. It gives the sum of the binomial distribution, like from 4 to 18. So answer is 0.9819. So this is the answer for this. And let's take the second option, sum of b binom 0 to 18 means it's a complete one. Like it tells all the values, like from 0 to 18, all are being defective. So this is not the correct one. Then it is like 1 minus f of x, like finding f of x and finding 1 minus f of x. This is useful. Generally, if we don't use the software, and if we solve by hand, what we generally do is like, instead of finding like 4 to 18, we will find an alternative way, like 1 minus probability of getting 0, 1, 2, and 3. So in this way, we will reduce the number of primes. Otherwise, we have to put NCR, P power R, Q power N minus R. We'll be doing it for 18, like, sorry, 15 samples. It will be like tedious job when we are doing it with the pen and paper. But when it is when it comes to the software, it is the computer is doing, so we don't have to worry about it. But still, just to know that there is another possibility or another way to solve this, we can do in this way: 1 minus sum of d binom. The 0 to 7 gives like 0 to 7 value, but it is not relevant to the current discussion. If it is from 0 to 3, then it makes sense. So this also gives the correct answer. It is like another way of solving the same problem. So let's go to the seventh question. Okay, let's go to the seventh question. Consider the problem described in the previous question. Which of the following plots gives the probability distribution function for four or more samples being defective? Okay, the for the problem, whatever we have solved before, they are asking like how the plot will look like. Um, and they have given many sample plots. Like I'm just going to tell you using the command how to generate the plot. So what command we have to use? We can just use the plot. We have to specify plot command. We know we have to specify x and y value. X value is ranging from 4 to 18, and it's a 15 character 15 values to be stored, and y values ranges from y value is given should be the probability. For that, we have to find the d binom for each and every value, like starting from 4 to 18. And we know the number of successes is the number of trials is 18, and probability of success, probability of item being defective is 0.1. And I have just labeling the x as k as they have specified in the same way they have specified in the graph, and y labeling is probability, and I'm giving the main topic or title as probability distribution. So when I give that, I get this kind of curve. So for whatever we have got the answer last question, for that we want to plot from 4 to 18. This is the plot we are getting. This is how the plot looks like. And the command is simple. Like we have to specify the x value, y value, then just labels whatever it is required. That's all. So this is the correct answer. Just match it with the question. So the other way, like I just wanted to explain if I change the parameters, how the plots will look like. The same plot what we have seen in the seventh question, if we change the probability value, the probability of success, the probability of finding a defective is high, they just change into a bell curve or normal distribution kind of curve. So as you can see, like when the 0.3, the curve started to see the bump. Then when it is like 0.6, it is having a bell curve. Then it is 0.8, it has started to skew towards the left. So the tail can be seen. In other words, we have as we have discussed before, when we are increasing the number of trials, like 100, the same with the same probability, it starts to approach the normal distribution curve. So this is another observation we can see. Like using this code, you can just play around and you can try to understand more clearly on the same context by changing the parameters and understanding the concept better. So because the software is doing, you don't have to worry about it. You can just try it out. So as we are moving towards the increase in number of population or increase in the number of trials or number of population data set, we fall into this continuous distribution. The most commonly used the continuous distribution is the normal distribution, because the normal distribution agrees with the most of the statistical data which we have. For example, a simple example is like if I distribute the people in a country in terms of their height, the it will follow like the people with, especially in India, people with 5 feet to 6 feet. If I take the cap, the and it's like 5.6 as the mean. We can see the most people will be in the 5.6. Then towards the right, it starts to decrease, and similarly towards left, start to decrease. And when we connect this, it looks like a normal distribution or the Gaussian distribution. People call it a Gaussian distribution because the Carl Friedrich Gauss defined this in the 19th century. It's introduced and extensively being used and till then. Okay, so the till now we were discussing about the probability mass function. From here onwards, it will be like probability density function because it is a continuous distribution. So the probability density distribution for the PDF, otherwise called as PDF for a normal distribution is given by P of x is equal to 1 by sigma into square root of 2 pi into exponential of minus 1 by 2 into x minus mu by sigma the whole square. Here the sigma is nothing but standard deviation, mu is nothing but the mean. So with this, let's try to solve the upcoming problems. Okay. Yeah. The eighth question. I think I have missed the eighth question. Question is this one. Seventh question is discussing the. Okay, that's the eighth question. Yeah. So the eighth question is like the PDF of a normal distribution is known as okay. For the normal distribution, the PDF probability density function is called as Gaussian distribution. Just now we have discussed. This was introduced by the Gauss. I forgot the name. Wait, Carl Friedrich Gauss. Yeah, Gauss. So it is popularly known as Gaussian distribution. In upcoming class, we will be discussing more in terms of this normal distribution. So I'm not diving deep into this now. Once the basics are done in the next upcoming thing, we will discuss more in detail. So yeah, going to the ninth question, the error function is related to. So the error function is like what is it? We can see the error function is given by 2 by pi. Error function of x is given by 2 by pi into square root of into integral of 0 to x into e power minus t square and dt. If you closely observe this, this looks similar to the Gaussian function or the normal distribution. Um, x minus mu by sigma the whole square instead of that t is being replaced. E power minus t square, and then you can see phi is also remaining the same. So this popularly this error function is the cumulative distribution of the standard deviation because the error function is the continuous. It's applicable only for the continuous variables. Here, if you see Poisson and then this negative binomial all are discrete, and CDF of standard normal distribution is given by the error function. So what is more interesting is like The usage of this error function. Error function is popularly used for finding the. It's popularly used in this mechanical engineering and civil for finding for modeling this thermal conductivity, and also in material science. The error function can be used to model the thermal conductivity of material as a function of temperature. So this can be done. Then diffusion. For example, near the surface, diffusivity, composition of a particular element near the surface will be high, but once we move along the x, the concentration decreases. C is equal to Cs, then the concentration decreases to Cm, the material composition. So this also modeled using this error function. This is popularly, if you are a metallurgist, you will can appreciate this. This is popularly being used in the um, finding the concentration of or the finding the concentration of carbon in case hardened steel from at a certain depth from the surface. And also the creep behavior is being popularly modeled using the error function uh, under constant flow. And risk assessment like the error function is used to model the uncertainties and probabilities of failure. So all these areas this is being used. I'll just take one example, popular example. It's like this I leave it to you. You can just solve using the error function whatever I have given. So a steel part is undergoing case hardening where the carbon is diffused into the surface. The process is carried out at a temperature of 173 Kelvin. So temperature is 73 Kelvin and duration is time 3600 seconds. Then the steel has initial carbon concentration of C0 per 1 watt-hour units, like this is called this 8% or 5%. Then CS on surface they have not given it since. See if they are given. No, they have not given. And we want to model the depth profile of the carbon concentration. CS, I think you can approximate it to like 28%. We have to model it, the concentration with respect to X after the case volume. It follows similar to this trend where the near the surface X is equal to 0. C is equal to Cs, like here 28 weight fraction. As it approaches the depth inside, starts to reach the symptom. There's nothing but C not initial configuration. So this is how the error functions are used. The error functions cannot be solved analytically because, as you can see, cannot solve it in pen and paper because it is not a simpler function like sin x or cos x, trigonometric or e power minus x or like nothing like that. It is like function of function, exponential of minus t square. So it's a function of function. So this cannot be solved using the analytical methods, pen and paper. So people sought for the numerical methods. So numerical methods include the um, Simpson's rule, trapezoidal rule, using that people used to solve this. Let me take a 5 minutes break. My throat is good enough. Let's proceed with the remaining questions. We try to solve this. If you have any doubts, we can discuss. Let f be the cumulative distribution function. If f of x is equal to q, x is known as, okay. So generally we define x as the qth quantile. For example, if it is 0.5, it is in the median. It divides the CDF into exactly half. Then if we specify 0.25, it is like the first quartile, 0.75 is the third quartile. So in a cumulative distribution function, f of x is equal to q defines the qth quantile. The last question. If pore formation is a problem in products manufactured by casting process, assuming that it follows Poisson distribution, the front, okay, it follows Poisson distribution. The front axle hub of a heavy-duty vehicle manufactured by casting contains 0.1 average force per square centimeter of the surface, considering an area of study. Okay, lambda rate is equal to, sorry, is it 0.1 force per square centimeter, considering the area of study of 100 square centimeters, the Poisson distribution of force for occurrence of 12 pores in the area. Okay. Study which of the following figures corresponds to the plot. Okay. First of all, we'll discuss how the one second. So the function which we use for this is dpoise. Let me copy and paste the program here. What I have done is like plot x, like as we have did before for binomial distribution. This is directly plotting, taking the value from 0 to 12 and Poisson distribution for exact values like 1, 2, 3 from 0 to 12, and Poise the x values is from 0 to 12, and uh, lambda into n. Here number of trials is like we have 100 squares, so it is 100 squares, so lambda into n or lambda into t number of times. So here t or n, whatever you keep it as, it's 100. So when we substitute, means when we give this command, we will be getting this kind of plot. So this closely resembles the some options they have given. So this is the one. So just you have to know how to plot using the probability distribution functions. That's all. Okay, let's discuss some additional problems. Since is there any doubt? If you have any doubt, we can discuss now. Otherwise, I have a few additional problems like that we can discuss. Let me know soon. Otherwise, I will proceed with the problems. Let's discuss some more problems before winding up. So, suppose a small machine component produced by a certain company has 0.005 probability of being defective, 0.5%. The company ships this machine component in a lot of 25. Size is 25. Each of the following R code snippets calculates the probability that a randomly chosen lot contains exactly one defective component. Exactly one means we can just use the density function. Sorry, d of d binom. So out of 25, one exactly one being defective is one. X is 1, size is 25, probability of probability of being defective is 0.005. So this gives the correct answer. So if they ask like uh, probability of getting one or no defective pieces, means we can use this p binom. So otherwise this is sufficient. This is sufficient. So I have not discussed this q binom so far, right? So like p binom, q binom, we can use it to find the quantiles. Like if I use the zero point 0.5 q binom of 0.5 comma size 20 comma probability 0.3, something like that, means it will specify. If I use here zero point 0.5, I will get the median. So it is used for specifying the quantiles. If I put 95, means 95 percentile of the data will fall in under that. 0.25 means first quartile, 0.5 means median, 0.75 means second quartile. Yeah, that's all. So R binom, as we know, it is used to generate the random variables along with random values given random variable, um, and then yeah, rest of things I've discussed. So let's go to the next question. In the above question, if you want to calculate the probability of at most one defective component, at most means one or less than one, means zero defective. As I discussed, it is P binom. If you use P, it will give the cumulative distributive function. So in atom probe analysis, atoms get knocked off from the specimen surface and are detected by the radial detector. Okay, they are telling the setup. Let's assume that M atoms are knocked off the surface of the sample. Out of the M atoms, only N atoms are being detected in the detector. Detector efficiency is given by Q is equal to N by M. This we have discussed before in before problems. One can consider the number of atoms M that get knocked off from the surface as real valued random variable denoted by M. It is also known as the M follows negative binomial distribution. Okay, with parameters N comma Q. Probability distribution of M can be written as this is a negative binomial distribution. This is what we have seen derived before. These are the following options will give the mean and random variable mean of the random variable M. So this mean is nothing but the expectation of M. So when we substitute all these things and when you do this um, simplifications, this the problem ends up at N by Q. So this can be further simplified by N. You can substitute plus N by M. So mean is nothing but the M. Now before simplification is N by Q. So this is the answer for this. Going to the fourth question. In the question 3, suppose the atom probe detector has an efficiency of 0.6 detecting an atom. The probability of 60% of efficiency, the detector efficiency, the probability of detecting 100 atoms when 150 atoms have escaped from the surface. As we know, like this follows a negative binomial distribution because it is about the detector. Detector efficiency is constant 0.6. We know dn binom. T binom is for cumulative. They are just asking the probability of detecting 100 atoms, exactly 100 atoms. When 150 atoms have escaped. So since it is exact, use dn binom. Okay. So x is nothing but the number of failures here, right? That one if you will see the syntax, x is the number of failure. So here it is 50. Size is the number of trials until the nth success. So it is 100 trials because 50 are failure, which means like 100 success. So number of trials until nth success is 100. Probability of success in each trial is 0.6. So this is the answer. Just know like what is the syntax for that. Here x is not the number of successes or detecting atoms. It is the number of failures. So 50 are failed out of 150 and 100 is trials until the nth success, 100 success, and probability is 0.6 efficiency of the detector. Let's discuss the next question. Suppose an urn contains 70 white balls and 30 black balls. What's the probability of selecting 14 white balls from the sample of 20 balls taken from the urn? So it is a fixed one, like whatever we have right now we are discussing is a 70 white ball. It has urn contains only 70 white balls and 30 black balls. So when we are taking 14 white balls from the sample of 20, when we are taking this 20 balls from an urn, out of which 14 should be white ball. then it is like taking without replacement. So without replacement means it follows hypergeometric distribution. So and they are asking 14 white balls from the sample of 20 balls selected. It's 20 balls totally being selected. So first we should know the syntax for the hypergeometric distribution. So d hyper is given by x is the vector of quantiles, the value at which to evaluate the PMF. Like 14 white balls have to be the probability of detecting 14 white balls. Probability of selecting 14 white balls is the x, and m is the number of successes in the population. So number of successes is like um, out of 100 black balls, we are selecting 70 white balls. So number of successes is 70 out of 100. So number of failures in the population is n, that is 30. So then the sample size, the total sample size for the x is 20. Out of the number of samples which we are taking out of the 100 black balls is the sample size, which is 20 here. So when we substitute all these things, the only option which are this close to this is A, this option. This is one which you have solved before, with quantity. That f of x is the cumulative distribution function, then median can be written as f inverse of 0.5. So 0.5 it separates the um, data from the center to equal number of variables. So 0.5 gives the first quantile, 0.75 gives the last quantile. Yeah, in the CDF function. That is from my side. If you have any doubts, we can discuss. Please feel free to ask. That's all. We are done with the session. So if you have any doubt, please send a mail. We can discuss further. I will keep this session alive for another 15 minutes. Like if you guys have doubt, you can ask.